Hello my dear champions, welcome to Deeksha Karnataka YouTube channel, and you are watching your favorite series Brahmastra 2.0, and in this series we are going to discuss magnetism and matter. It is a small chapter, but trust me, from this chapter if you study it will be very easy for you to score marks. The questions are very short, and if you study few of the questions you can answer all the questions that will come from this chapter. And also we have done an extensive research, and that research is put into our Brahmastra series. So if you are watching this series for the first time, don't forget to share this with your friends so that all of you can score well. And remember that PU2 is going to be very essential if you are preparing for your KCET exam. So for KCET exam as well as your board exam, so this series is the utmost important series for all of you, right? So without much delay, let me start with today's series, and thank you for showing trust in us, and definitely it will help you in a long run. So if you have missed some of the videos that going to have that already published in your channel, so don't miss out on them. So those are very important chapters, essential chapters, and we are discussing only the important questions that you are going to get from each and every chapter. So if you are lagging behind in your PU2 preparation, for example your FA2 exam is coming soon, then there will be your pre-board exam, so everything will be covered in this series. So let's see into the blueprint of this chapter. So if you see here we have 1 marker questions coming from this chapter is 2, not 1. So far all the chapters that I have discussed, only 1 questions was coming from 1 marker section, but from this chapter 2 question is coming from 1 mark as a 1 mark question. But from the blueprint that we have studied, we realize that and as well as the model question paper and previous year question papers, after studying everything we realized 1 MCQ question will come from this chapter and 1 fill in the blank. So not 2 MCQ question, okay? So 2 questions coming means 1 question is from your MCQ and 1 question is for your fill in the blanks, right? So a short answer type 2 marker question is not going to come from this chapter, only short answer type 3 marker question is going to come from this chapter, and total marks allotted for this chapter is 5. So if you watch this short video, it is not going to be a very long video. So if you watch this video, all 5 marks you can definitely guarantee it from this chapter. So this is the question breakup. So as usual we are going to discuss 15 very important hand-picked selected MCQs. We will also discuss 5 fill in the blanks and 10 3 marker questions. So as you can see, all questions will be covered here from this chapter and nothing will be left behind. So if you watch this video, your entire PU2 preparation will be done. So let's start with the first question. So question number 1, in the following table, column 1 is the list of magnetic property and column 2 is the list of an item related to magnetic property. Identify the correct match. So you have to find the correct match between the following table. So in the column 1 some properties are given, for example paramagnetism, diamagnetism, ferromagnetism, and in column 2 some of their properties are given. So let's see, magnetic property common to all substances. So what property is common to all substances? The common property among all substances is diamagnetism. Diamagnetism is common to all substances, okay? Next, domain formation. Now which material shows domain formation? Only ferromagnetic substances shows domain formation. So domain formation is associated with ferromagnetism. Now sodium is an example of this magnetic property. So even if you don't know what type of material sodium is, so from after elimination you can easily see that it is definitely going to match with paramagnetic substance, okay? So match the following questions are maybe sometimes tricky, but if you can at least find 50% of the matches, remaining 50% you can either guess from the option or you can guess from the whatever is left, okay? Now let's find the match. 1 is matching with R, so we will look for 1 is matching with R. So this is option B, 1 is matching with R. Option C is also 1 is matching with R. 2 is matching with P. 2 is matching with P, but here 2 is matching with Q, so definitely this is not the correct match. So correct match is 1 is matching with R, 2 is matching with P, and definitely 3 is matching with Q. So correct answer option B for this question. Right, now let's move on to the question number 2. The ferromagnetic material among the following is, so you have to find the ferromagnetic material. Copper is not a ferromagnetic material, nickel is a ferromagnetic material, lead and calcium, they are also not ferromagnetic material, only nickel is a ferromagnetic material. So remember 3 metals: copper, iron and cobalt. Okay, they are 3 materials which are directly ferromagnetic. There are some alloys obviously, but these 3 are in elemental form are ferromagnetic in room temperature. Okay, copper, nickel and iron. Gadolinium has a transition temperature around room temperature, but gadolinium only below room temperature can be considered as a ferromagnetic, not at room temperature. Okay, now next, the physical quantities related to magnetism are listed in the column 1 and dimensions are listed in column 2. Identify the correct match. Now sir, this is a very difficult question. I don't have any idea about dimension. So what to do about in that case? So you have to remember some of the few easier dimensions and hope that only one option is given from that option. So first of all, magnetic field can be tricky. Magnetic permeability trickier. Magnetic moment easy. Magnetic moment is current times area. Magnetic moment is given by M equals to current times area. Okay, there is a number of turns involved, but number of turns is a dimensionless quantity, so current into area is the major thing. So what is the dimension of current? Dimension of current is ampere. Dimension of area is meter square, so definitely it will be L square A is the dimension of magnetic moment, so this is directly matching with this. Okay, so 3 is matching with B. Now let's see what are all the options given in this question. So if you see that only one correct option with 3 with B, so this is 3 with C, 3C, 3A, 3B. Only one correct option with 3B, definitely this is the correct answer. And if you forget 1 is matching with C, that means the magnetic field's dimension is given by this one and permeability dimension is given by this one. Now one thing you can remember is that out of magnetic permeability and magnetic field has 1 less ampere compared to magnetic permeability. Permeability and magnetic field are almost same, only difference is in the dimension of ampere. So ampere or current dimension is -1 for magnetic field and it is -2 for permeability. Okay, these two are very close to each other, so sometimes it gets confused between what will be the dimension of these two quantities. Okay, also in magnetic permeability there is a length involved, in magnetic field length is not there. Okay, so these two things you can remember, otherwise at least try to find the common dimension and try to figure out what will be the other two dimension. And remember that generally, one more point to remember, generally direct match is not given in the match the following question. Okay, so direct match, so for example 1 is matching with A, very less chance of giving it like this. Okay, so from if you find one match, remaining 2 matches will be easy, at least for 3 match the following type question. So one match is this, that means it cannot be matched with this, so it should be matched with this, and this one will match with this one. Okay, this is a technique or trick to match the following type of question. Okay, another match the following type of question, and all the match the following type of questions are given in your current model paper. So this is also from your model paper, so be sure you practice the questions, those are match the following type. Okay, based on the magnetic properties, materials are listed on the column 1 and values of magnetic susceptibilities are listed in the column 2. So this is magnetic materials and this is their susceptibilities, so easy match the following. Let's see what is the option here. Okay, so diamagnetic substances have negative susceptibility, so small and negative is the match for diamagnetic. Paramagnetic substances have small and positive, so this is the match, and for ferromagnetic this is the match. large and positive. Okay, this is easy question. Now let's see the option. 1 is matching with R, 1 is matching with R, only one option is there where 1 is matching with R, 2 is matching with the P, and 3 is with Q. So correct option, option B. Okay, not a difficult one. Now let's move on. The SI unit of magnetic flux. What is the unit of magnetic flux? From Gauss's law we get to know about magnetic flux. Magnetic flux is the SI unit of magnetic flux. There are two units. One is Tesla meter square, or this is also called Weber. This entire thing is also called Weber. Okay, so Weber or Tesla meter square is the unit of magnetic flux. So Weber is the correct answer for this question. Universal property amongst all substances. So what is the universal property? This is from 2024 PYQ. Universal property among all substances is diamagnetism, and this question you will be able to answer only if you read the NCERT completely. So from NCERT this question came, but again I am here, I am helping you to understand all difficult questions that you need to answer. So universal properties among all substances are called diamagnetism. Magnetization of a sample is magnetic moment per unit length, magnetic moment per unit area, magnetic moment per unit volume, magnetic moment per unit current. So magnetization is defined by total magnetic moment or M net divided by the volume. Okay, it's a vector quantity, so it is the sum of all the vector magnetic moments divided by the volume. So it is magnetic moment per unit volume. Okay. Next question, the net magnetic flux through any closed surface is 0. This is in accordance with Gauss's law of magnetism. Gauss's law of magnetism. So this is talking about magnetic flux. So definitely it is magnetism, not electrostatics. Okay. A magnetic dipole of magnetic moment is placed in a uniform magnetic field such that the angle between magnetic moment and magnetic field is theta. So it will be mentioned M and B is theta. Okay, if the magnetic dipole is in the stable equilibrium position, then theta is equals to 0, theta is equals to 90 degrees, theta is equals to 180 degrees, theta equals to 45 degrees. So what is the torque acting on a magnetic dipole? Torque acting on a magnetic dipole is given by MB sine theta. Okay, MB sine theta. So if it is in equilibrium, then the torque must be 0. So torque can be 0 in two positions. One is theta equals to 0, another one is theta equals to 180 degrees. Okay, but which one of them is stable position? For stable position you need to know the potential energy as well. What is the form for potential energy? Potential energy is MB cos theta. Okay, both are important to know. So stable equilibrium, what is the theta for equilibrium? Theta for equilibrium is theta equals to 0 as well as theta equals to 180 degrees. These two angles gives the equilibrium because torque becomes 0. So understand this. Okay, even though it's an easy question, I am trying to explain the concept so that you memorize it, you remember it. Whenever if the question comes a little difficult, so same question is asked when it will be unstable equilibrium, you will know, you will be able to answer it. So stable equilibrium means when torque is 0. First of all, equilibrium means torque is 0. Now whether it will be stable or unstable, that depends on the potential energy. So what is the potential energy at theta equals to 0? So potential energy at theta equals to 0 is given by minus MB. Cos theta is 1. What about the potential energy when theta is equals to 180 degree? So in that case, potential energy will be plus MB. Why? Because cos 180 degree is minus 1. So minus minus plus, so it will be plus MB. So potential energy is negative and lowest. This is the lowest value of potential energy. In case of stable equilibrium, potential energy has to be lowest, and in case of unstable equilibrium, potential energy is highest. Okay, so as you can see, this is the highest potential energy, this is the lowest potential energy, and 0 is not the lowest potential energy in this case. Okay, anything negative is less than 0, that means it is smallest. So this is the smallest potential energy, that means theta equals to 0 gives the stable equilibrium. equilibrium, whereas theta equals to 180 degree gives the unstable equilibrium. Needles N1, N2 and N3 are made of ferromagnetic, a paramagnetic and a diamagnetic substance respectively. A magnet when brought close to them will. So we have needles N1, N2 and N3. Okay, and first one is ferro, second one is para, third one is dia. Now you brought a magnet. Magnet means it is a permanent magnet, so it has north south pole. So what will happen? So this magnet will definitely attract this one. Okay, attract the north, attract the ferromagnet. It will even attract the paramagnet, but it will repel the diamagnet. Okay, so this is strong, strongly attract, it will weakly attract, and diamagnet will be again weakly repel. Okay, so it will attract N1 strongly, N2 weakly and repel N3 weakly. So this is the correct answer, option B. Make sure if you are confused to draw this small diagram. Okay, this kind of questions are very common nowadays. Even in KCET exam some years back this question came, and it is given in your question bank as well. So now let's move on. The susceptibility of a ferromagnetic material is, susceptibility of ferromagnetic substance is much greater than 1. So correct answer is option C. Again, this is from your PYQ of last year. Which of the following properties is false for a bar magnet? Okay, so there are 4 properties. 3 of them is correct, 1 of them is incorrect. It does not produce magnetic field. So a bar magnet will definitely produce magnetic field. So that means this is the wrong statement. This is our correct answer. Its poles cannot be separated, correct statement. It points in the north-south direction, correct statement. It like poles repel and unlike poles attract, this is also a correct statement. So 3 of the statements are correct. First statement is wrong. So that is our answer for this question. A susceptibility of a certain magnetic material is 400. What is the class of the magnetic material? So susceptibility, we know that if it is very greater than 1, then it's a ferromagnet. So 400 is definitely very greater than 1. So this is must be a ferromagnetic material. Next question. The magnetic field lines inside a bar magnet. So magnetic field lines inside a bar magnet, what happens? We know that for a magnet, the magnetic field lines outside a bar magnet moves from north to south. Inside the bar magnet, it goes from south to north. So are from south pole to north pole. Inside the bar magnet, it is opposite to that of outside. So inside the bar magnet, it goes from south pole to north pole. So option B is the correct answer. Now question number 15. When a bar magnet of dipole moment m vector is placed in an uniform magnetic field, then what is the torque acting on it? Calculate the torque acting on it. The torque acting on it is given by m vector cross b vector. This is the expression for torque acting on a dipole moment, on a bar magnet or a magnetic needle. Okay, the torque is given by m cross b, not b cross m. Okay, it is m cross b. Now let's move into the fill in the blanks section. An example for dimensionless quantity is, so let's see what are all the quantities mentioned in this option. Diamagnetic, solenoid, magnetic susceptibility, magnetization, paramagnetic, ferromagnetic. So only quantity that is mentioned over here is magnetic susceptibility. So definitely this is the correct answer for this. So magnetic susceptibility is a dimensionless quantity. The magnetic susceptibility is negative for dash material. So here we have 3 materials: diamagnetic, paramagnetic and ferromagnetic. All 3 materials are given as an option. So magnetic susceptibility is negative for diamagnetic substances. Okay, it is positive but small for paramagnetic, and it is positive but large for ferromagnetic substance. Okay, so correct answer for this is diamagnetic. Now a current carrying dash is equivalent to a bar magnet. So let's see what are all options left. So we already have diamagnetic sorted, magnetic susceptibility sorted. So we have solenoid, magnetization, paramagnetic, ferromagnetic. So which one will be the option here? A current carrying solenoid is equivalent to a bar magnet. So that is only thing that makes some sense. So always I told you, I says that multiple times, whenever you are doing fill in the blanks, say check if the option is making any sense or not. So here only solenoid is making a sense. So definitely solenoid will be our answer, and we will effectively mark it. Next question, the net magnetic moment acquired per unit volume of a sample is called. Again, if you see the remaining option, we have magnetization, paramagnetic, ferromagnetic. Only magnetization is making any sense over here. So magnetization will be the correct answer for this question. So correct answer is magnetization. 20. The magnetic susceptibility is slightly positive for dash materials. So magnetic susceptibility is slightly positive for paramagnetic substances. Okay, so correct answer is paramagnetic. Now let's move on to 3 marker question. There is no 2 marker question. Now in your FA2 maybe you will see some 2 marker question, possibly some 2 marker question from this chapter, but don't worry, you can answer those 2 marker questions if you study these 3 marker questions. All the questions will be knockoff version of this 3 marker question. So here they will ask you 3 differences. In a 2 marker question they will ask you only only 2 differences. Now this question is basically actually 3 questions. Okay, this one question is equivalent to 3 questions: diamagnetic, paramagnetic, diamagnetic, ferromagnetic, paramagnetic, ferromagnetic. So any combination of difference might come, and this is very common, very popular question. If you take the PYQs, this question has came multiple times, and not only any 2 of them, diapara, diaferro, paraferro, all 3 of them has come in the past. Okay, so here is one slide, one page answer to every question that might come from this chapter. So practice them very by heart them, and remember it is very easy to remember anyway. So what is the property? First is property magnetic behavior. They are weakly repelled by magnetic field. Diamagnetic substances weakly repelled by magnetic field. Paramagnetic substances, these are weakly attracted by magnetic field, and ferromagnetic substances, these are strongly attracted by magnetic field. Now magnetic susceptibility, for diamagnetic substance it is small and negative. For paramagnetic it is small but positive. For ferromagnetic it is positive and large. Okay, next is effect in a magnetic field. Induces a magnetic field, magnetic moment in the opposite direction of the applied field. Here induces a magnetic moment in the same direction of the applied field. Here induces a magnetic moment in the same direction, but it is a very strong magnetic field in the direction of applied magnetic field. Okay, now next question, mention any 3 properties of magnetic field lines. Another very common question, possibly asked multiple times again. So any 3 properties, easy question. The magnetic field lines of a magnet form continuous closed loops. The tangent to the field line at a given point represents the direction of the net magnetic field at that point. The magnetic field lines do not intersect, for if they did, the direction of magnetic field would not be unique at the point of intersection. So let me explain the third point, but before I have to explain the second point. So if you have a magnetic field line like this, and if you draw a tangent at any point, that line gives you the direction of magnetic field at that particular point. But suppose 2 field lines intersect at some point, okay, then what will happen at the point of intersection? At the point of intersection, we will have one field line in this direction, another field in this direction. So 2 separate field meeting at a same point. So practically what will happen? Practically they will not give you neither this nor that, but you will get a resultant magnetic field which will be like this. Okay, so these 2 field lines will never exist, and you will not get a crossover of two field lines. Even if you bring two magnets closer to each other, they will give you a resultant field, not a crossing field. Okay, so two field lines will never cross even if they are coming from two different magnets or more than two different magnets. They will never cross each other. Okay, remember that, because magnetic field is a vector quantity and it has a uniqueness. What is a uniqueness? Every vector quantity has a unique direction. Any vector quantity, okay, any vector quantity is unique and they only have one direction, not multiple direction. Define magnetization of a sample, how it is related to magnetic intensity. Magnetization M of a substance, magnetization M of a substance is measure of the net magnetic moment per unit volume of the material. Okay, so it is given by M equals to net magnetic moment divided by volume. Okay, relation between magnetic intensity and susceptibility is given by M equals to chi H. Okay, here chi is called magnetic susceptibility. Okay, chi is called magnetic susceptibility. The pronunciation for this is chi. Okay, state and explain Gauss's law of magnetism. Another very common question. Gauss's law for magnetism is very easy. Unlike Gauss's law for electrostatics, magnetism one is actually 0 on the right hand side. So whenever we see 0, except for marks, we feel happy, right? So if you see 0 in your mark sheet or score sheet, you get disappointed. But if you have to write the 0 as an answer, maybe for an MCQ, maybe for a question answer, then we feel happy because we don't need to do too much for it, right? So this is one of them. So the net magnetic flux through any closed surface is 0. Okay, that is the major thing, and you can write a small s over here. Physical significance. What is the physical significance? Magnetic monopole do not exist. Okay, so in case you see any magnetic monopole, then it would have been magnetic monopole by mu naught or mu naught into magnetic monopole moment, but that is not there. Magnetic monopole do not exist. So on our right hand side, we can easily write 0. Okay, magnetic field lines always form closed loop. Okay, so magnetic field lines always form closed loop. That means whatever exit from north pole, it will not only go to south pole, it will also come back to north pole via inside route of the magnet. Okay, that is the major difference between electric field and magnetic field. Okay, now which materials show perfect diamagnetism? Write the susceptibility and relative permeability values for such material. So again, this is a question from your model question paper, latest model question paper. Superconductors show perfect, not model question paper, sorry, it is from question bank. This question is taken from your question bank. Superconductors show perfect diamagnetism. Superconductors, okay, so far we have not discussed too much about superconductors, but this question is given in your question bank, might be coming, but easy question, not super difficult to remember either. That's why I decided why not include it. Superconductors show perfect diamagnetism. For such materials, magnetic susceptibility is exactly equals to -1. Remember this, for superconductors, susceptibility is exactly equals to -1, and you might see one MCQ question also can come from this information. Okay, one MCQ question can sometimes come from this information. Also, superconductors are called perfect diamagnets. Okay, they are also sometimes called perfect diamagnets. Why? Because their susceptibility is -1. So remember this simple facts. Okay, so they are called perfect diamagnets. Relative permeability exactly equals to 0. Relative permeability is exactly equals to 0. Now next, derive the expression for magnetic potential energy for a magnetic dipole placed in an uniform magnetic field. Now you might seem this is a new question. Actually it is not. It is the same derivation for electric dipole. Only difference is that the terms are different. Okay, so in case of magnetic dipole also, electric dipole also, we did this derivation. Okay, not the torque but the magnetic energy. Okay, potential energy. Suppose we have a magnet inside a magnetic field. So this is north, this is south. Okay, and when you place it inside a magnetic field B, okay, there will be a torque that will act on it. And if you want to derive the expression for torque, it is same as electric field. Only thing you have to take magnetic monopole moment for individual poles, strength of individual poles, and then you have to calculate it. But here for this case we do not need to do that. What we will be doing, we will be directly taking the expression for torque. Now for electric field, if you remember, torque was given by PE sin theta, PE sin theta, okay, but for magnetic torque it is given by MB sin theta. Okay, sin theta is same, only instead of P we are writing M, for E we are writing B. M is magnetic dipole moment and B is magnetic field. Okay, now initially suppose this thing was at an angle theta. Okay, initially it was at an angle theta. Now if you slightly rotate it by a small angle, if you rotate it by a small angle, say d theta, then how much work you need to do? The work that you need to do is given by dw to rotate the needle, magnetic needle, we are assuming magnetic needle or magnetic dipole, okay, to rotate the dipole by a small angle theta, d theta, the work done is dw. Why we are taking small rotation? Because as you know, torque depends on the angle theta. So if you change the angle by very large amount, then the sin theta value changes drastically. That value of torque will also change. But if you change it by very small angle, we can still consider the previous torque is still acting on it, and we can apply the formula for work done, which is given by force into displacement for normal case, torque into angular displacement for rotational case. Okay, torque into rotational displacement in case of rotational motion, force into displacement for linear motion. So this is the small angle d theta. So the work done is given by MB sin theta d theta. Okay, now what is the total work done? Total work done must be equals to integration of this entire thing. Okay, that is our technique. Okay, we do integration. What is the meaning of integration? Integration represents taking small portions and adding it. Okay, so we will take small angle d theta 1, d theta 2, d theta 3, and corresponding sin thetas also we will take, and we will add them, then we will get the integration, right? Integration is basically type of addition. So what is the angle? What is the starting point? Starting point has to be where the potential energy is 0. Generally we consider potential energy is 0 when it is at an angle theta equals to 90 degree. Okay, theta equals to 90 degree or pi by 2, that we consider as our 0 point. So here we will start at theta equals to pi by 2 and we will end up at some angle theta. Okay, so from pi by 2 to theta, how much work we are doing? Starting point, ending point. Now let's do the integration. So MB is constant, by the way, so it will come out of integration. So only integration is left is sin theta d theta, and limit is pi by 2 to theta. Now what is the integration of sin theta? By this time I hope everyone has completed the integration process and already aware what is the integration of theta, sin theta, right? Like unlike in your PU1 when physics teacher was trying to teach you integration, differentiation, you are thinking what is this? This is a completely hard subject. I am not able to understand. But now everything is very much easier because you think, okay, physics, mathematics is much easier compared to that of mathematics, right? I hope you have the same feeling. We all had gone through this situation once in our life. Okay, so MB, W equals to MB, and integration of sin theta is minus cos theta. Okay, it is minus cos theta. Now we will put the limit pi by 2 to theta. Now how to apply the limit? First we will apply the upper limit is theta, so minus sign we are taking common, okay, minus sign we are taking common outside, so cos theta is again cos theta only, and minus the lower limit cos 90 degree or cos pi by 2. Now what is the value of cos pi by 2? Value of cos pi by 2 obviously 0, so we get work done is minus mb cos theta, and this work is being stored as the potential energy of the magnetic dipole. So the energy of the magnetic dipole is basically minus mb cos theta. Okay, so this is the expression for energy, and if you do this small derivation you will get full 3 marks. And as you have already understood, this is nothing different than that of electric dipole. Only thing is the names are different. In case of electric dipole it was PE, it is MB in magnet. Okay, nothing else is different, everything is same. Now list any 3 properties of paramagnetic substances. Now this is the same question that we have done in the previous one, that when we are doing the difference table. So if you remember the difference table, you can still answer this question. Okay, these are nothing different than that of the difference table. Okay, but this question can also come, so you have to prepare your mind about this. The 3 properties of magnetic substances: these are weakly attracted by magnetic field, they have small positive magnetic susceptibility, these materials introduces a magnetic moment in the same direction as the applied field. So these are the 3 properties. Next, list any 3 properties of diamagnetic materials. 3 properties of diamagnetic substances are: they are weakly repelled by magnetic field, they have small negative susceptibility, these materials induces a magnetic moment in the opposite direction of the applied field. List any 3 properties of ferromagnetic substances. 3 properties of ferromagnetic substances: these are strongly not repelled, strongly attracted by magnetic field, strongly attracted by a magnetic field, they have a large positive magnetic susceptibility, these materials introduces a strong magnetic moment in the same direction of the applied magnetic field. Okay, so these are the 3 points of ferromagnetic materials. Now what are hard ferromagnets and soft ferromagnets? Give example of is easy question. Hard ferromagnets: in some ferromagnetic materials the magnetization persists even after external magnetic field is removed. Such materials are called hard ferromagnetic materials or hard ferromagnets. Example: alnico, steel. These are examples of hard ferromagnets. Soft ferromagnets: these is a class of ferromagnetic materials in which the magnetization disappears on removal of the external magnetic field. Such materials are called hard magnetic materials or soft ferromagnets. Example: soft iron. Okay, soft iron is an example. Another one is, you can say, pig iron. Okay, soft iron, pig iron, they are example of soft ferromagnetic materials. So this is the end of this lecture. I hope you enjoyed, and definitely I request you to subscribe to our channel, and obviously thank you for showing trust on us, and we will strive to deliver the best content for your PU2 as well as your KCET exam. So if you are watching this for the first time, definitely I would like to request you to subscribe to our channel, and definitely join the WhatsApp group. The link of the WhatsApp group is given in the description section of this video. There we will be sharing all the important updates and all the PDF lecture PDFs exclusively in our WhatsApp channel. So I thank you for watching. I will be back with a new chapter very soon. Till then, bye.